Hi, everyone. Thank you for joining us for today's seminar. It's a special member benefit opportunity for AIA California members. My name is Yin Wayne. I'm an AIA and member of the educational subcommittees, and I'll be your moderators and a part of a presentation presenter today. As you all know, AIA California has developed this in-depth series focusing on understanding and implementing the AIA framework for design excellence. This series has offered 26 webinars so far this year. As always, all webinars, content, and additional resources will be available on the AIA California website shortly after each session. Additionally, more information on the final two climate action webinars for the year will be shared in your follow-up email. So a few quick housekeeping reminders before we get started. Please using the Q&A. Can you move on to the next slide, Sarah? The Q&A functions, thank you. To ask any question for today's presenters, you can also like a question to move it to the top of the queue. Today's session qualifies for one AIA HSW learning units. And for those watching live, and so make sure you stay put until the end of a presentation. And the AIA California staff will report those units for you. The session is also being recorded and will be posted on the AIA California website, and additional resources and PDF the presentation shortly after today's session. So we start today's session. So why we are here, three of us here. It's three of us made of one architect, one engineer, and one emerging professionals of science specialists and engineers. Anyway, and behind us, there are tons of people are very interested with what we're doing, and what we're putting on is really of many people's effort. So we're talking about the reason, or a short reason, for us to have this study is because of the COVID. All of us gone through the COVID, we still not finished COVID, plus the wildfire, to put us into really serious thinking head. What's so important of, we are all basically 8 hours, 24 hours, so 24 hours in building facility every day. And those two things really impacted. And the big part of it is HVAC's design. So move on to the next one. So the two people with me, James Sui and John Cole. James has been well known in Southern California. Many of you probably saw his building or reside in the building he designed. He's big in K-12 LAUSD school districts build a project, a lot of it done by James, or the standard developed from James's expertise. He's also very involved in the medical field, so involved with a lot of LA County the medical facilities review and the board on that site, plus very special conditions projects like the Santa Monica, I think the Performing Arts Center is the recent one. So his expertise involved a lot on this very special project to the very regular one that you see every day, impact a lot of populations. John Call is a very special friend of us. He is kind of coming from the left side. He is a computer science based, and actually this company Comfort is his third entrepreneur project or endeavor. and you will see his products, and it's just excellent. I would just bring very quick of what he did one before is many of you go into the hotel and you put your key in, right? Then you walk in, then the lights are starting to turn on. And that was one of John's effort to make things a lot more only being used when it's needed. So in this newer one, it's the same concept, do not waste when you're not using it. The next one. So we get to all of us as regular folks or as architect, now we suddenly realize how important the air quality is, not only inside the building, because that's what I used to be only care about it, but now I understand how to read this PM level in my smartphone all the time. Is whenever there's wildfire, we know that we make sure my area is better than the other area or worse than the other areas. So that's all part of the things that James is going to cover today. The other part is ozone is another one that's all becoming our daily encounters. The next one. So we're talking about healthier buildings through HVAC. So I would like to remind every architect right now, we're only focusing on the HVAC, forget about our beautiful exterior design, right? Let's just focus on that. So from the COVID and the wildfire, we understand a couple of things is now let's make sure the outdoor air ventilation rate is preferred. And that's kind of covered in the Title 24 more and more that you can see it requires you to have OSA. The second one is cleaning the recirculated air through higher performance filters. Again, that's aligned to Title 24, aligns to LEED. You see that requirements are just getting tougher and tougher. And the third one is because of the COVID, we understand we need to have those special devices that can clean up or just kill those viruses. We're talking about UVC and the other type things is a plasmid and PCO. And I think those areas that probably would take another seminar to talk about the differences from among all three of them and where do you put it in order to get most effectiveness. The fourth one is using smart control to facilitate the buildings and the occupancy needs. That's really connect to what John calls devices help us out to that level. Move on. Next one. So a little bit, just a brief kind of a taste appetizer for architects. Like me, I'm never really quite clear with, I understand code, I understand Title 24, and I don't never walk into the mechanical in a way. I'm pretty on top of the energy code. And then ASHRAE 62, ASHRAE 655, it's like, what's the difference? So we're just kind of understand there is those background contexts that we are abide by. So 62 is always indoor air quality, 55 is thermal comfort. And I think both of them are related to when we're talking about the energy code. The newer concept, what James will bring a little bit for you to understand where he comes from, is these two things called PMV and PPD. PMV is predicted mean vote of occupant comfort. So bring down to, get your eyes, bring down to the next bullet. If PMV says 6 variables, humidity, air, speed, clothing, we usually don't consider that. Air temperature, metabolic rate, radiance, and human comfort. So that's right away brings the architects a wider view of it's more than the mechanical that we're talking about. It's the people who residing in your building that you need to really consider it. The last one is the newest. It's not the new things. It's always there. It's just hardly being really taken seriously into a way to practice your HVAC design. is the adaptive comfort model, because what it takes into more than the PMV that's above pointed out, it does bring you the idea of look at the climate, look at whom you are dealing with, which is a social and psychological and behavior adaptations. All of this kind of bring to this PMV and PPD is a combined science and artwork in a way. All right, move down to the next slide. So here is why we hope that we'll be able to pass all those information to you today, and in order for you to say, yes, I'm comfortable with those knowledge. The first one is implement mixed mode, or what does that mean? This very simple way of describing is just natural ventilation and the mechanical design are interact all the time, is comprehensive design. The second one is using this adaptive mode to increase this occupancy satisfaction. And then the third one is to be able to comply with, we're talking about this ASH rate, which is very kind of foreign to us, and also the CDC guidelines. The fourth one is the necessary ending of the HVAC enhancement in the existing building to combat the COVID and or to improve the tenants' comfortableness. Okay, so next one. All right, CDC. And from this part, James will take over the presentation. Go ahead, James.
Hi, I appreciate being able to give this seminar. Okay, most of the materials come from the management information reports that I was commissioned to do right, say near the start of the pandemic. I do a lot of institutional work, say I do schools, I do medical buildings, I do performing arts centers, things of that nature. So the CDC guidelines, I think, are derived from the ASHRAE guidelines. So I'm just repeating what Ying was saying. Okay, you need more ventilation, more outside air, because COVID infections are, say, from aerosols that you breathe out in an enclosed space. So to get the aerosols out, you need to dilute the air in the room with more ventilation, more outside air. And then you have to move the air more in the space, higher air circulations, so that the air mix better. And of course, see, if you have more outside air, you have to get it out. So you have to exhaust as much as possible. And you can afford to just have 100% outside air all the time. So you have to recirculate the air. And when you recirculate the air, you have to really, really clean it. And with the wildfires and a lot of areas that I work in, say have dust problems in the desert. So you really, really have to clean the supply air. So that's filtration and, say other means of air cleaning. So, and then your HVAC system only work as well as the controls. So you really, really need good controls, good sensors, and a good sequence of operation. Next slide, please. Okay, so this is where the CDC recommendations are based on. The ASHRAE position document on infectious aerosols. So I'll cut right to the chase. Dilution with outdoor air ventilation, I've already said that. Airflow patterns, okay, so air movement, say where the air is moving, how it is moving, say how well it mixes. And pressurization, that's kind of very important in hospitals. Say some areas are positive, like an operating room needs to be positive. A small utility room needs to be negative, and some areas need to be neutral. And temperature and humidity distribution, that's a no-brainer. And control strategies. I think this is the most important in an HVAC system. Let me repeat, and your system only works as well as the controls. In air filtration, this is kind of ignored in most commercial buildings, especially the smaller ones. And now it's in the code. Okay, Title 24, the 2019, Title 24 requires you to have at least MERV 13 filters. MERV stands for minimum efficiency reporting value. Okay, so it tells you see how efficient a filter is. So MERV 13 is pretty efficient. A hospital filter is about MERV 15 or 16. 16 is very close to HEPA, okay, which is a high efficiency, particularly in arrester. That's very, very efficient. And in addition to filtration, we are adding, UVC lights. The UVC lights have been used for a long time to, prevent mold growing inside the air conditioning unit. But you need a lot stronger UVC to set an airstream. So none of the add-on technologies are mature as yet. We're still trying to decide which one is the best. And we only have the manufacturers to get the information from. So there's plasma ionization, photocatalytic oxidation, a lot of new technologies. But filtration works, and activated carbon filter works, and UVC works if you have enough of it. So next slide, please. Okay. And before the pandemic, because I live in a very temperate area, Southern California, most people are trying to bring the outdoors indoors when weather is, fit, okay, conducive. So a lot of the air conditioning systems that we design have two modes, okay? If the outdoor weather is favorable, you open the doors and windows and whatnot. And we use natural ventilation. And I do a lot of work for the ports also. So we have rain sensors, wind sensors, and outdoor air quality sensors. And these sensors warn the building occupants or automatically close, openings and stuff if we have, like window master products and whatnot. When outdoor weather is extreme and we go to the mechanical cooling mode. Okay, so I personally tested, and just opening the windows a crack improved the outdoor air quality. And the natural wind velocities are found to provide sufficient outdoor air ventilation to dilute the indoor pollutants. So next slide, please. Okay, so I've applied natural ventilation, two different ways, passive and fan assisted. For the passive approach, if you have cross flow and enough window openings, or just door openings or whatever openings, okay, that works. And the Title 24, the current Title 24 has prescriptive requirements, okay, prescribed for passive outdoor air ventilation. And to do that, you have to start say when the architect is positioning the building and study the say outdoor air, say wind patterns and where we place the say intake openings and where we place the relief openings stuff. And next slide, please. Okay, so with natural ventilation, very passive, say cross flow plus stratification works also. If you have a high building, a high ceiling, say, and if you have an opening, say at the roof level for, say just gravity relief, the natural stratification of air, works. Okay, but if outside is stagnant, you can go to the fan-assisted approach. So what I've been doing with existing buildings is if you have 100% outside is economizer system, you change the controls so that you can open the windows or you can open dampers, louvers, whatever, say, which can, say allow outside air in, and turn on the exhaust fan to, say create air movement. Okay, and I have done quite a few gyms. I do a lot of gyms, say because I do schools, and I recently completed the design of a community center, which is a gym and community rooms for the city of Los Angeles. And there I have a mixed mode ventilation system where the airflow is assisted by wind-powered fans. So the wind-powered fans are fans with motors, which take advantage of outside air velocity, say wind velocity. And if there is enough wind, say the motors won't draw any current at all. Okay, and some of these have are solar powered. Okay, next slide, please. So again, mixed mode ventilation. HVAC systems for mixed mode ventilation, they should have 100% outside air economizer systems. And most systems nowadays have 100% outside air economizer systems and MERV 13 filters. And we would like to have plasma ionization systems or UVC, whichever, see, I usually work with MNO departments for institutions, so they have their preferences. So plasma ionization is new, and it's a lot of people claim that it's not proven. Okay, and UVC has been around for some time. Next slide, please. Okay, and these, say graphics are developed by the Institute for the Built Environment, okay, of UC Berkeley. So these are the recommended modes of mixed mode ventilation. Okay, so the changeover design, which is prevalent, and I've done a lot of these. Okay, and then the concurrent mixed mode operation is, say not very common, but I've seen a lot in Asia also. And the zone system is kind of rare. I've never done it, but this is a concept presented by IDE. Okay, and Ying asked a question about plasma air cleaners. Okay, those are, say electric plasma generators, and there are two types, say those which generate ozone, which are not preferred at all, and say the modern ones which are not supposed to create ozone. And what they do is they ionize the air and say make the particles in the air stick together more so that they could be caught in the filters. And they've been around for some time. You see, I used to do a lot of casinos when smoking was allowed in California. Okay, and at that time we used a system called the positron, which can zap the tobacco smoke particles in the air and make them coagulate, and we can catch them in, like, say, MERV 14, 15 filters. But those systems require a lot of air changes. They need about 15 to 20 air changes to work. Okay, next slide, please. Okay, and this is a relatively new concept, and ASHRAE adopted into the ASHRAE Standard 55 only in 2004. So in our industry, you know, say that is relatively new. Okay, the ASHRAE Standard 55 was done in, I think, 1955. So it is not very commonly applied here, but because I come from a very poor country, you know, say it is used a lot over there. Okay, so the adaptive model is based on, you know, say people's adaptivity, you know, say based on their behavior, their physiological changes based on weather, and also psychological. So you need to educate the people first. And most manufacturers want us to just use one criteria, temperature. And the conventional thermostats have been designed around temperature. So everybody nowadays accept that, oh, we need between 70 and 75 for us to be comfortable in summer. So, but you don't take into account, you know, say you can dress differently and you can adapt to the weather, because they even, you know, say ASHRAE Standard 55, the old one, okay, you have two charts, one for summer and another one for winter. In Title 24, you know, say we usually use 68 or 70 degrees as winter design and 74 degrees as summer design, because, you know, say our bodies adapt and the way we dress change with the weather. Okay, so the adaptive comfort model research, you know, say has shown that occupants of naturally ventilated buildings accept or even prefer a wider range of temperatures. So if I go to like Santa Monica 3rd Street Promenade, a lot of the restaurants there, you know, say just open up in, you know, say all the walls, most of the walls have, you know, say these very big doors, and they reduce their air conditioning, and it seems to work. Okay, I don't see too many people complaining. So next slide, please. So this is a little bit more about the adaptive comfort model. Outdoor climate influence indoor comfort as humans adapt to different temperatures during different times of the year. I've already mentioned that. The adaptive hypothesis predicts that contextual factors such as having access to environmental controls, if you can control the environment yourself, if you can control your temperature from your phone, you know, say people will feel better. And past thermal history can influence building occupants' thermal expectations and preferences. User experience varies depending on individual background. Occupants in naturally ventilated buildings accept a wider range of temperatures and humidity. Okay, so next slide, please. So this is what I was talking about. Let's say the ASHRAE Standard 55 chart. So if you look at the chart, you'll see two trapezoids. okay? And the bottom axis is the operative temperature, which is not the real measured temperature, but a calculated value, which is derived from the air temperature and also take into account air velocity and radiation from the surrounding objects. So the old-fashioned thermostats only consider temperature. Okay. But ceiling fans use air velocity to cool a person. And for natural ventilation, let's say we would sometimes oversize the exhaust fans. So if you need, let's say, say 5 air changes to cool with 55-degree air, you can use 65-degree air to cool the same space if you have 20 air changes. And it might even feel cooler because of the air velocity. And radiation from surrounding objects. This is sometimes the biggest say problem for us. If you have a meeting room, a conference room with a lot of glazing and not enough shading, even if you have a lot of air blowing into the space, say if the sun shines directly on a person, you're hot. So the operative temperature takes air temperature, air velocity, and radiation from surrounding objects into account. And we couldn't apply it properly in the past because we didn't have good enough sensors. So let me get back to the chart. So you only need to worry about the bottom axis, which is the operative temperature, which I just explained about. And then the curved lines, which are relative humidity lines. Okay. And the two trapezoids that you see are the comfort range of a person. So the right one is for summer and the left one is for winter. That's what I mentioned a few slides ago. Okay. So in summer, people can be, say comfortable at 83 degrees operative temperature when the relative humidity is below 10%. So people will be comfortable at 80 degrees operative temperature if the relative humidity is below 60%. So the common design temperature for Title 24 and say it's about universal, say 74 degrees F, say dry bulb, and about 50% relative humidity. And above 60, say there could be mold problems. So, but people are comfortable within any temperature relative humidity combination in this little trapezoid. And the left one is for winter. So it ranges from 68 degrees to, say 78 degrees, which is, say a no-brainer. Okay, but people can be comfortable down to 68 degrees. Okay, but say you need to humidify the space. So that's why say most of the buildings in the bigger buildings, the better buildings in the Midwest and the East have humidifiers. Okay. We don't have to humidify a lot because we don't have a lot of heating here in Southern California. So, but if it is very dry, you need to be a little bit warmer. Okay, next slide, please. Okay, this is only for heating operations. Okay, and I experienced this in restaurants with higher ceilings and a lot of school gyms. Okay, when you heat in winter, the hot air rises. And if, say we have a gym class and we have a lot of kids, say running around on the floor, the hot air rises more and it hugs the ceiling. So we have to spend more energy to, say heat the space because of stratification, the bottom part of the room cools. So, say the first idea was to use ceiling fans and blow the hot air back down into the occupied space to cool this, heat the space and decrease energy. Okay, and then it evolved during the COVID to, can you go to the next slide, please? Okay, devices like these, which are air cleaners, which are suspended overhead. And this little thing that I have on the slide has a HEPA filter, a UVC light, an activated carbon filter for VOCs and odor, and titanium oxide filters. So this is probably a relatively expensive device. But, say during COVID, say a lot of these are, say sold, and a lot of people use that to destratify the space. Next slide, please. Controls. I'm repeating myself again. Any building system is only as good as the controls. So when we try to upgrade an existing system, okay, we start with the controls. And the controls have evolved to a point. A good control system can maintain both indoor environmental quality and energy efficiency. Okay, for indoor environmental quality, you cannot just sense the temperature. You have to sense the humidity, carbon monoxide levels. Say if you have fossil fuels inside the building, say CO sensors are a code requirement in California now. Okay, carbon dioxide, VOCs, particulate matters, especially say when you have a lot of traffic outside or wildfires. Air movement is usually not measured, and radiant heat effects. Okay, so we need say new sensors, a new generation of sensors to incorporate all these for good indoor environmental quality. And then that is not enough. We need to sense the outdoor conditions. We cannot just leave an air conditioning system in 100% outside economizer mode when there are wildfires burning outside. So if the outdoor conditions are not conducive to better indoor environmental quality, we have to change over. So that's where the mixed mode ventilation and better controls come from. And for energy efficiency, occupancy sensors. Okay, occupancy sensors can be really, really effective. Okay, John will tell you about it in this presentation. See, just using occupancy sensors and turning off the ventilation and say set points in unoccupied spaces would save a ton of energy. And also training, okay, to optimize pre-occupancy warm-ups and cool downs, and when we need to restart the equipment to say have the space cool enough or hot enough after say occupancy sensor shutdowns and stuff. Okay, so that's important. And setback and setup, we don't need to do that a lot here in California, but it's in the code. If outside gets very cold, it will be wise to start the HVAC system and heat the building so that the building will be, it won't take forever for the building to warm up when you occupy the building in the morning. Okay, just maintain a certain temperature where the building can recover fast enough from. Okay, the same with cooling. Okay, we apply two strategies. If outside is cool enough at night, and if the building has a lot of mass, you can just turn on the fans and circulate air inside the building to cool the mass of the building, so that you'll use less energy to cool down and maintain the space temperatures. Okay, so that's setback and setup. And machine learning, AI, say nowadays, say we have new technologies. So next slide, please. This is John's. So I'll hand over to John now. Thank you.
Great, thank you, James. Appreciate it. It's good to be here and meet everybody. My name is John. I'm the founder and CEO of Comfort IQ. We're a startup company. I think we've created a pretty cool and innovative system for large commercial HVAC systems. Some of the benefits that we bring, and I'll go over the technology here in a second, but some of the benefits that we've brought is over 50% HVAC energy savings. We've fixed all the hot office, cold office problems that a lot of people have to deal with today. And our system also has continuously monitors indoor air quality as well. Like James said, we've implemented a lot of the principles that he's talked about here with regard to the mixed mode ventilation, as well as the adaptive model for comfort. So the first example, I'm going to give you guys a couple examples. Really, I'm here to take some of the ideas that have been spoken about today and turning them into real life, real world application, and some of the results that that we've discovered through some of these pilots and projects that we've done. Many of you guys will know this campus. It's the LADWP Lacretz campus in downtown LA. We, in partnership with LADWP, the Los Angeles Cleantech Incubator, as well as us, piloted our microzone system in this building earlier this year. I think we began in about July or so. Wanted to get some knowledge about the potential energy savings, as well as the improvements on occupant comfort, as well as monitoring the indoor environmental quality as well. Can I go to the next slide, please? So just to cover a little bit of the technology, what we've done is this is the East building, I believe. We installed our system in all of the enclosed offices as well as conference rooms as phase 1 of the project. We're beginning phase 2 in the open space work environments next month. And a little bit about the technology, but what we did was we installed sensors in every single one of those offices. They are smart sensors. The primary purpose, which is not just to detect occupancy, but we're collecting a lot of different points of data, including temperature, humidity, occupancy, obviously, CO2, VOC, as well as sound and light intensity. Because our goal is really to look at the human experience on the inside from a holistic perspective. And that's some of the things that we are working toward. Essentially, and I don't want to get too much into technology because I only asked for 4 minutes, but we're very similar to putting a Nest in every office. And we're collecting a lot of that data, and primarily what we're doing is creating behavioral and thermodynamic models of every room. And then we're taking that and maximizing energy efficiency, as well as in consideration for tenant comfort as well. So this is some of the adaptive model stuff that James is talking about. So we studied the data for a period of 3 months. It is metered data. I believe the system is vertigris. It is a rooftop unit by Aon, I believe 70 ton. We installed, again, as phase 1 in about 10,000 square feet out of the 28,000 square feet that's available in this building. And as you can see the results there, we measured over that period of about 3 months, 33% energy savings, but you have to note that we were only installed in about 30% of the space. And this is equivalent to about 90%, over 90% in HVAC energy savings. When we did our comparison, we only looked at 2 things. We looked at the temperature outside, as well as the kilowatt hours used on that rooftop unit. And we did compared data within COVID. So I believe we compared data from August with similar dates in July and June, as well as September and October dates as well. And there's a couple of interesting things that we learned, actually. We did remove the heating and cooling loads from unoccupied spaces, and that's where we got a significant portion of our energy savings. But we also got a significant portion of energy savings by making people feel more comfortable, by preventing the overheating and overcooling of rooms. I don't have any hard data. We're about to do that survey here soon. But according to Stephen Hargett, who's the facility manager there, we have fixed most, if not all, of the temperature problems. They have no more complaints about temperature issues. And obviously, we've saved a ton of energy there as well. Can we go to the next slide? So the second example, the bottom is just some of the data that we got from our dashboard system. But it was really interesting because this building was experiencing spikes in CO2 and VOCs almost every morning, and sometimes for hours on end. And initially, we had thought that it might have been a data issue or something. But after talking to people, we called the facility manager over there and we asked questions. We found out that what was happening was that there is a maintenance yard that is adjacent to that building. And the guys who were coming into work every morning were firing up their diesel engines. And that exhaust was polluting the air of the building next to it. And so we found this out. It was a really neat discovery by looking at the data. We're happy to have found it. But now what we're doing is we are proposing our mixed mode ventilation solution to optimize their HVAC system. It's a package unit system for using the outdoor air to improve the indoor air quality and obviously the energy efficiency. And what we're going to be doing is we're going to be monitoring some of the outside conditions such as air velocity, the weather, rain, air quality, particle matter. And obviously, when the air quality is good, we're going to open up that the damper or the economizer to let in more fresh air, especially when the air is much cooler outside. We need cooling inside, and basically run our algorithms to provide more fresh air when it's healthful to do so, and to optimize energy use at the same time. So, so these are two examples of the adaptive model for occupant comfort and the mixed mode ventilation. James and I have been collaborating for several years now on this system. What you're seeing here, what I tell people is that you're seeing the first stage in a system, in a building management system that used to only care about making sure that every room got a certain amount of airflow, never really regarded people's comfort issues or anything like that, or their individual comfort issues. And this is the first step in changing these types of systems into one that focuses on energy efficiency and the health and well-being of the people inside. But as I said before, we are a startup. We have about 8 plus or minus installations throughout Southern California and the rest of the USA. We are looking for pilots. So if any of you guys are out there wanting to check out our system for maybe some of your customers or even for your offices, and to test drive our solution, then come find me on LinkedIn, or yeah, you can stick around for questions, or maybe I'll share my information on the chat screen there as well. So with that, I'm going to hand it, I think, back over to Ying. Ying?
No, I think it's back to me, right?
Oh,
Yeah, so
to rehash the best practices.
yeah, James, we have 10 minutes left, so I'm not trying to wrap it pretty fast.
Yes.
Yes.
So actually, say, let me run through this very fast. See, it's a rehash of what I've mentioned before. Best practices: increase outdoor air ventilation, reduce cross-flow air circulation, recirculate with high-performance air filtration, device to neutralize germs in the airstream, UVC, plasma ionization, etc., exhaust fans and smart control, better sensors, 100% outside air economizers, And radiant heating and cooling works with dedicated outside air systems. Okay, next slide, please. For existing buildings, that is where I get the most questions. Natural ventilation, if you have operable windows, and stratification, if you have higher ceilings. Fan-assisted outdoor air ventilation, that is not commonly used. I don't know why. See, I use that a lot. And good control strategy. Okay, and during COVID, see, everybody asked about increased ventilation. We changed the controls so that the building works with 100% outside air and revert to, say a minimum ventilation only when the equipment capacity is exceeded. And use of better sensors and additional measures to neutralize airborne pathogens. UVC, plasma ionization, catalytic filters, oxidation, things of that nature. Next slide, please. Okay, and the importance of outdoor air quality monitors. To do a good, say a mixed mode ventilation system, or if you want better indoor environmental quality, you need to have outdoor air quality monitors. Okay, and the last thing is, say during the pandemic, see, I tried in residences just cracking the windows open a little bit and measuring the air quality. And even a little crack, say if you have a sliding window and if you leave like 2-3 inches open, the air quality improves dramatically. So next slide, please. Okay, this is Ying. Conclusion.
Thank you. Super quick and super clear, I hope, for everyone. For older architects like me, usually stay away from anything dealing with engineering, that you have a general common sense. Basically, it's kind of tied into this passive design, energy efficiencies, the tenants' health. It's all connected together and become a resilience future in a way. So hopefully that if we run out of time for any of the question and the answer, I see quite a few in our box, and I did answer a few already. So here is, take our last shot of our contact information on the bottom, and you're very welcome to contact with us. And we appreciate such a big opportunity for us to share what we understand from our profession to all of you. And so thank you, AIA. Since AIA will submit your credits, C credits automatically, it should occur right away. And so again, the information that we share today will be in the AIA website. Thank you, AIA. And we'll see you next time. Thank you. Oh, so I need to go to the question and the answer. Sorry.
Yeah.
So, Huang, what's your opinion regarding the proposed? Do I have to talk about this one? Hunger Hall at UCSB, not using any natural ventilation. Sucks. That's my answer. James, you can answer it. So it's basically a huge cube without any windows for dormitory, but it's some guy said, I pay for all of it, but you take my design. That's what happened. So it's a lot of architects and the lead people all protest right now. So this is the most hot subjects right now. Okay, so I'll leave that. I'll just read the question first. Then second, how do you decide where to locate the outdoor air quality monitors? I think that's specific to James. The third one, if individual users can open or close the windows at will, is that compatible with a mixed mode system? And can sensors detect whether a manual operate window is open? So great questions. The next one is from cameras for ice rink, 92% enclosed. We're adding through wall gable fence in opposite ends of the rink enclosure serve to adequately potentially dilute the SARS-CoV-2 virus in that facility. We were concerned and it could exacerbate, I have a hard time on using that word, the spreading of the virus. So
Yes.
I think number 4 is for James right away, and the number 3, I'm going backwards, and the individual uses to James, and I think also the number, how do you decide where the monitor is? All 3 goes to James, and the first one I think is just goes to everyone about the hunger board.
Okay, so let me start with, I'm supposed to start from the top, right?
From the top, I end up forgot the wrong notes.
Yeah.
So just read it. Yeah.
So at present, see, there are no standards. That is the problem. Okay, there are recommendations, see, and we are trying to follow standards. But just my thinking, see, because see, I've been practicing for like 40 years, or a little bit over 40. And having very rigid standards also, I think, limits innovation and imagination. So having standards is good. Okay, then everybody can perform up to a certain standard, but there should be some freedom for innovation. So what do you think, Ying?
Oh,
Because I do a lot of institutional work, say all these district standards and stuff. I think they are stifling.
I don't worry that, because this is really architect specialty, is to fighting the authorities. I think it's coming with our nature of our business. We do have a time limit. So if we run out of time, I don't know when AIA is just going to shut us out, but we promise you we will answer all the questions.
Yes. So my answer is I don't like prescriptive. I've never done, say prescriptive approach for Title 24 ever.
Good answer.
And where do you locate the outdoor air quality monitors? Okay, the outdoor air quality monitors that I've used before, it's not just one device, see, it's many different devices. So the rain sensors, the wind velocity sensors and stuff, say you only need one for each building. So, say there's one which is connected to the energy management system. The humidity sensors, temperature sensors, they come with the economizer. Okay, and the new sensors, I think, say if it is controlling the quality of the outside air, it should be at the outside air intake, say, and feed directly to the controller of the unit. It depends on the cost, see, if it is very costly, say you can just do it with one for the entire building, or if it is a small building. But if you have huge air handlers, say you want them to be independent. So if it doesn't cost a whole lot more, say it's simpler to have outdoor air sensors at the outside air intake of every air handler. I hope that answers your question. Okay, and individual users can open or close their windows at will. If you do retrofits, you have to do it, see, and the outdoor air quality sensors just warn the occupants that, hey, outdoor air quality is not so good, say you should close the windows, okay? And, say that's for smaller buildings. And Title 24 requires, say door and window proximity switches and whatnot. So if you have that, say you can integrate and come up with a sequence of operation. So you can do it either way. So last Cameron. Okay. So airflow, say if you have cross flow, air movement is supposed to dilute and move the aerosols out. So that's our understanding. So hey, say what ASHRAE and CDC recommend is increase the air change rate, have more air movement in the space, have more outside air, and if possible, don't recirculate the air. So if you have, say supply fans on one side and exhaust fans from the other side, doing push-pull, I think, say, but you could be blowing, say somebody's breath from one end of the rink to the other end. So I'd rather exhaust from the top and make up from the bottom from all sides. That's a way I would do it, say not just blow from one side to the other. And last question, we can filter and open windows, at least not very efficiently. So that's why we need outdoor air quality sensors in the mixed mode operation. For naturally ventilated buildings with, say, people like Price sell outdoor air, say, louver damper combinations with built-in, say, say water coils and electric coils and whatnot, and electrostatic filters. So those can help a little, not, say to 100% satisfaction, get rid of some of the outdoor polluters like dust and stuff. And we use it only for gyms. At least I've only used it for gyms. I hope that answers your question. Okay, any more questions? I think that's it, right?
There's one question from Q&A from Frank James. He's asking, can you use in filter higher level of filter to replace the use of UVC?
Better filtration, I prefer better filtration. Only problem is, see, the higher filters require a lot more fan power. So when you do it in a retrofit situation, say you are limited in a fan static pressure. And sometimes, say like when we do LA Unified clinics, okay, we have to follow OSHPAT, but OSHPAT doesn't do plan check. DSA does. So we still have to beat Title 24. So we have to use electronic filters. So there's more than one way to kill the cat, say. So better, I prefer better filtration than UVC, say to make it work, say it's kind of difficult. I have to use a 10 feet length of duct full of UVC lights. And, say these are expensive and you have to be maintained. So I vote for filters. Better filtration. If you don't have enough, say static pressure, use, say people like Dynamic. Say there are a lot of manufacturers in the market, and some of them are OSHPAT approved for higher filtration. We can use them in hospitals and stuff.
Good question, Frank. You can see how James totally agree. The devil is in the detail. So we're coming down to the conclusion of today, and thank you everyone joining us, and appreciate the AIA support, and love John's and James' presentation. Have a very good day, everyone. Bye-bye.
Thank you.